In this video, I'd like to discuss the uniform continuity, which is a stronger version of a conventional continuity. So, let me first remind you the concept of continuity, the conventional continuity. Say suppose f is continuous at some point x naught in the domain of the definition, which can be understood for any epsilon or any positive epsilon, there is this corresponding delta such that for any x in the domain of the definition, if the distance between x and x naught is smaller than delta, that implies the distance of the value f of x and f of x naught. This difference is estimated by epsilon. Okay, so for given at a specific point x naught, for any epsilon, you should have the corresponding delta. And the choice of delta usually depends on epsilon. If your epsilon is small, then your corresponding delta must be small quantity. In addition to that, the choice of delta also depends on the position x naught. Choice of delta depends on both epsilon and x naught. Okay. So let's consider this example. Say suppose we have a function f of x, which is given by 1 over x squared, whose domain of definition is positive real numbers. And I want to show this function f is continuous at some point x naught. This is a positive real number. So what you want to show is for any epsilon, there exists the corresponding delta such that if the distance between x and x naught is smaller than delta, implies f of x and f of x naught. This difference is estimated by epsilon. Okay. So for given function 1 over x squared, we need to consider this excuse me, this quantity. Now let's consider the difference f of x minus f of x naught. Okay, which is 1 over x squared minus 1 over x naught squared, which can be converted into, to make the denominator together, we're going to have x squared, x naught squared minus x squared divided by x squared. Excuse me. And we can factor the numerator to get x naught minus x and x naught plus x and x squared and x naught squared. Okay, to get the estimation for this kind of expression, we're going to choose delta and for consider the x whose this difference between x naught and x is smaller than the quantity delta. So we can control this term, the size of this term. Okay. Then what about the other terms? Here we have additional x, and the x is also in the denominator. So for 0 and x naught is somewhere on the positive real axis, and if x gets close to 0, then this quantity gets bigger, since we have a xx in the denominator. So what if we consider x naught be half of x naught? We consider the delta neighborhood as the neighborhood of center that x naught with the radius half of x naught. So if x minus x naught, this difference is less than x naught f of x naught. Then this variable x belongs to the interval from x naught half of x naught to 3x naught over 2. Okay, which means this term x naught plus x, this term in the numerator belongs to the interval from 3x naught over 2 and 5x naught over 2. Okay, then f of x minus f of x naught. The difference between those two terms. The difference, okay, we're going to compute the absolute value of this expression. Then we have the absolute value of this term, and to get this inequality, okay, we're going to replace this term something bigger than this one, okay, which is this quantity. So this term will be replaced by 5x naught over 2. Okay, and here we have x naught square. And to get this inequality, we're going to replace x, the variable x, in the denominator by something smaller than x itself. So if you replace this x by something like this, we're going to have x naught squared over 4. Okay? Then this will be written as, okay, we have 10 and x minus x naught, yes, the value of x minus x naught over x naught cube. Okay, so if we have the estimation like this, if this quantity is smaller than epsilon, then we are done. Okay, to get this kind of inequality, we need to choose delta. What's the corresponding delta? We're going to move these terms to the other side to get x naught cube times epsilon over 10. But to apply these inequalities, we need an additional condition for x, which means your delta must be smaller than this one, too. So you take the delta as the minimum of this quantity and x naught over 2. Okay, then you can use those conditions and this estimation simultaneously. Okay, and if the distance between x and x naught is smaller than delta, we have this estimation. This difference is bounded by epsilon. Okay, so here we have epsilon. If we choose smaller epsilon, your delta must be smaller. Okay. However, the choice of delta also depends on the position x naught. Okay, this function itself is continuous on the entire positivity axis. However, in this proof, the choice of delta, even for a fixed epsilon, if we fix the epsilon, the choice of delta depends on x naught. Okay, this delta should be small for small. Actually, the situation gets clear by looking at the graph of this function. Okay, this is the graph of f of x, which is 1 over x squared. For any x naught, this function is continuous. Okay, for any positive x, here we have f of x naught. Okay, so for fixed x naught, you're going to first choose the point of interest x naught. Then at this point, for any epsilon, okay, you're going to choose the appropriate delta to make. We're going to use different color. Okay, for any epsilon neighborhood centered at f of x naught, there exists corresponding delta. Okay, the value of the function for these variables belong to the interval from x naught minus delta to x naught plus delta will be moved to somewhere in this epsilon neighborhood. Okay, that's the continuity. Okay. However, if your x naught gets closer to the origin, if x naught is located somewhere around here, then the corresponding value is somewhere around there. If you choose the same epsilon as here, okay, the same neighborhood, the choice of corresponding delta now must be much smaller, right? The same region, I guess, will be moved to somewhere, something like that. Okay, in this region, this delta neighborhood, okay, the neighborhood of the radius delta corresponds to something like that. But around here, the same range for the delta neighborhood, okay, centered at x naught, will cover much bigger value. Okay, which means to show the continuity, your choice of delta must be even smaller, depending on the choice of x naught. Okay, that's the typical situation for the continuous function, usual continuous function. And we're going to define the uniform continuity. This uniformity means that the choice of delta is independent of the location x naught. Okay, so the idea of uniform continuity, the function f is uniformly continuous. Delta does not depend on x naught. Okay, so let me give you a rigorous proof definition for the uniform continuous. A function f whose domain is S, a real valued function defined on the domain of definition S, is uniformly continuous. If and only if for any epsilon there exists delta such that so here we do not have a specific point x naught. For any epsilon, there is this corresponding delta such that x and y, both of them are variables in the domain of definition. If this difference is smaller than delta, that implies f of x and f of y. The difference between the value is bounded by epsilon. Okay? So there is no fixed point x naught at all. This single delta, this delta depends on epsilon. However, this delta does not depend on any value in the domain of definition. There is no fixed point. Okay? For this delta, if the distance between 2 points in the domain of definition is smaller than delta, the corresponding value, the difference of the corresponding value is smaller than arbitrary epsilon. Okay? uniformly continuous at x norm. This kind of expression is nonsense. Okay, there is nothing like uniformly continuous at a specific point. Okay, uniformly continuous. The uniformity means all over the domain, not a specific point. Okay. So let's get back to this example again. 1 over x squared. Okay, let me restrict the domain of the definition from 0 to 1. This is not uniformly continuous. Okay, the graph of the function that starts from number 1, from 0 to 1. So the graph of the function is this part. Okay, this function is not uniformly continuous. Okay, how can you verify this property? The uniformly continuous has been defined by this way. Okay, then to show the negation of that kind of proposition, you have to take the, okay, what's the negation of this proposition? There exists some epsilon. Here we choose epsilon as number 1. For this specific epsilon, for all delta, okay, the existence will be converted into the for all delta. Then, okay, what about this statement? For any epsilon, there is delta such that here x and y, these are, we have the condition like this. For all x and y in the domain of definition, if they satisfy this estimation, we're going to get the result like that. So the negation, as a negation, here we fixed epsilon as number 1, and for all delta, for any kind of choice delta, there exists x and y in the domain of definition from 0 to 1, such that, okay, here we have the proposition of P implies Q, okay, which is equivalent to not P or Q. And its negation is P and not Q. That means x minus y. This difference is smaller than delta. And f of x minus f of y. The difference between the value is now greater than or equal to epsilon. This is number 1. Okay. So for any delta, no matter how small delta is, we're going to show the existence of such x and y, whose difference is smaller than delta, and the difference of the value, difference of, okay, this is 1 over x squared minus 1 over y squared. This difference is greater than 1. Okay, how can you choose such value? The choice of such x and y may depend on the size of delta. Okay, this must be true for all delta. So we're going to consider these 2 different cases when delta is greater than 1/2. Then we can choose x is 1/4 and y is 1/2. Okay. Then x minus y. This difference is 1/4, which is smaller than delta. But f of x minus f of y, which is by applying the function like that, we're going to have okay, 1/4, 1 over x squared. And then if you put 1/4 for x, we're going to have 16 minus. So this difference is greater than. Okay, so it's easy if delta is big enough. bigger than 1/2. But if delta is smaller than 1/2, of course it should be positive, then your choice must be more careful. Then you're going to consider x and y. Okay? When delta is very small, we're going to choose x and y. Both of them gets very close to the origin. Okay, so we're going to choose that x as delta itself and y as 3 delta over 2. And that's the difference. The difference is half of delta, which is smaller than delta. But f of x minus f of y, this difference is 1 over delta square minus. This one gives us 4 over 9 delta square. Okay, which is 1 over delta square multiplied by, okay, this is 9 over 9, so 5 over 9. Okay, and delta is less than half. This is greater than 4 times 9 over 5 over 9, okay, which is greater than 1. So this function, 1 over x squared, is not uniformly continuous. Later on, we're going to show this function is not uniformly continuous, even using more simpler way. But this is here. This is the proof for the non-uniformity, non-uniform continuity based on the original definition. Here, let's consider a continuous function whose domain is closed and bounded. Okay, a closed and bounded domain, which is also known as compact set. A compact domain is very good for us to handle a continuous function. If the domain is compact or closed and bounded, the continuous function turn out to be uniform continuous function automatically. Okay, so continuous function on a compact set is uniformly continuous. The entire domain of definition. Okay. Again, we're going to rely on the induction. If the result, the conclusion is false, we're going to derive a contradiction. So suppose this function f is not uniformly continuous. Then there exists delta, there exists epsilon. For this epsilon, for all delta, there exists x and y in the domain of definition, such that this difference, x and y, the difference between x and y is smaller than delta, but f of x and f of y, difference of the value is greater than or equal to epsilon. Okay, again, the negation of the uniform continuity. Then there exists some epsilon, and for all delta, we have corresponding x and y. So for delta, it's chosen as 1 over n. Okay, if you choose delta, since this is true for all delta, if you choose delta as 1 over n, there exists x and y, the corresponding x and y will be denoted by xn and yn. xn and yn in the domain of definition such that the difference between xn and yn is smaller than 1 over n. And f of xn and f of yn. This difference is greater than or equal to epsilon. Okay? Here, this is a bounded set. And xn, the collection of xn is a sequence in this domain. And similarly, that yn is also a sequence in a bounded set. A sequence in a bounded set has a very nice property. By the Bolzano-Weierstrass theorem. Okay, what is that? Bolzano-Weierstrass theorem tells us any sequence in the bounded domain must have a convergent subsequence. We're not saying the sequence itself converges. Okay? Even though the domain is bounded, any sequence can oscillate. It does not converge to a fixed value. However, a bounded sequence must have a convergent subsequence. Okay? So there exists a subsequence x sub n sub k. And this subsequence must converge. There exists the limit of x and k. Okay? As k tends to infinity. And this limit will be denoted by simply x naught. Okay? Here we use the boundedness to apply the Bolzano-Weierstrass theorem. And now we use the closedness. Okay, the domain of definition is closed. This interval is closed and boundedness. We use the boundedness to apply the Bolzano-Weierstrass theorem. And closedness will be used like this. Since the domain is closed, okay, as I mentioned before, the closed set, if you have closed set, any sequence, any convergent sequence in the closed set cannot get out of that set since it is closed, right? Which means the limit value x naught cannot get out of the set, original set, like this. Since this is closed, the limit x naught belongs to this closed. Okay? And, excuse me, the distance between xn and yn gets smaller and smaller, which implies this yn also converges to same limit. Okay? We also have the convergence limit of yn. No, actually, not the original sequence yn, the subsequence ynk with the same index. There's x and k converges to x naught. And x and k, the difference between x and k and y and k gets smaller and smaller. So this subsequence also converges to x naught, the same limit. Now, we're going to use the continuity. The function, original function is continuous. Okay? Which means, excuse me, the value of the function is the same as the limit of f of x and k. Since x and k converges to x naught, the corresponding value of the continuous function also converges to its value. Okay, and this is also the same as the limit of f of y and k, since they converge to same x naught. Okay. However, this contradicts to this estimation. But f of x and k and f of y and k, this difference must be always greater than or equal to a fixed number epsilon. So they cannot converge to the same limit. Excuse me. Okay, since the difference between those two values are always greater than some fixed number epsilon. they cannot converge to the same limit. So this is a contradiction. Now let's ask this kind of question. Say suppose Sn is a Cauchy sequence. Let me first start with a continuous function. Say suppose f is a continuous function whose domain of definition is denoted by capital S. And we're going to consider Sn is a Cauchy sequence in the domain of definition. Then, if you evaluate function f over this Cauchy sequence, you're going to get a sequence of real numbers. Okay? By applying a continuous function to a Cauchy sequence, you're going to get a sequence of real numbers. The question is, does this application of continuous function to Cauchy sequence preserve the Cauchy property? Is it a Cauchy sequence or not? The answer is negative. No. And you can easily construct a counterexample. Suppose f of x is given by 1 over x. Positive number, and Sn is simply 1 over n. Then this is a Cauchy sequence, right? It eventually converges. A convergent sequence is a Cauchy sequence. Although the limit gets outside of the domain, the sequence itself is a Cauchy sequence. And f of Sn is simply n, which is not a Cauchy sequence. This is Cauchy. This is f of Sn is not a Cauchy sequence. That's the usual situation for the continuous function. So a general continuous function does not preserve the Cauchy property. The uniform continuous function, which is even stronger version of continuous function, the uniform continuity preserves the Cauchy property. Okay. It means, let's suppose f is uniformly continuous, and Sn is a Cauchy sequence. In this domain of definition, then f of Sn. This sequence is again Cauchy sequence. Okay. Let me first use the uniform continuity. Since the function is uniformly continuous, for any epsilon, there exists delta such that for any x and y in the domain of definition, if this difference is smaller than delta, we have f of x and f of y. This difference is smaller than epsilon. Okay, that's uniform continuity. Now, let's use the Cauchy property. Since Sn is a Cauchy sequence, in the domain of definition, okay, a Cauchy sequence has this property. For any constant epsilon, there exists big number n, such that if you have indices n and m, greater than the threshold, the difference between Sn and Sm, okay, the difference between any tail element gets smaller than an arbitrary constant. Okay, Cauchy property usually stated with epsilon, but you can choose an arbitrary constant. Okay, for any constant, there exists big number n. Okay, in the tail element. whose indices are greater than n implies it must have this kind of estimation. From this estimation, I'd like to have f of Sn and f of Sm. This difference gets smaller than epsilon. Okay. What's the appropriate choice for this blank? You can choose delta. This delta. Okay. And for any epsilon, there is big number n. If the indices are greater than factor n, then the difference between those values are smaller than epsilon, which means by combining those parts, you're going to have the Cauchy property of f of Sn. Okay? So, a uniformly continuous function preserves the Cauchy property. And this function, the previous example, is not uniformly continuous. Okay, we have verified this non-uniformity. This function is not uniformly continuous by using its original definition, epsilon and delta. However, you can show the same property, same condition, by choosing a Cauchy sequence. If you choose Sn as 1 over, then this is a Cauchy sequence. However, f of Sn, which is simply n squared, this is not a Cauchy sequence. So, f is not uniformly continuous. Okay. Now, we are interested in the, okay, let me review this property. If the function, a continuous function defined on a closed and bounded interval, turn out to be a uniformly continuous function automatically. Okay, then if the function is defined on the open interval, and we know the continuity, then this one does not imply the uniformly continuous, uniform continuity in general. We need some additional condition. Okay, if the domain is open interval. Okay, as we have seen, yes. Well, okay, you can restrict the domain as the interval from 0 to 1. The function, this function is not a uniformly continuous function. So, a function defined on an open interval must have additional condition to satisfy the uniform continuity. Okay. This additional condition can be described by using what's called the extension. What if we increase the domain of definition, this open interval, as a closed interval? If you increase the domain by putting both endpoints, you're going to convert this function with the domain of definition into a closed interval. So we want to somehow enlarge or make bigger the domain of definition. This kind of process usually referred to as what's called the extension. Okay. F is a function okay, whose domain of definition is explicitly denoted by dom of f. And f tilde is an extension. An extension is a function whose domain of definition is bigger than the original function. That means the dom of f and dom of f tilde has this set inclusion relation. However, the value of the function on a common domain must be the same. F of x agrees with f tilde of x for x in the original domain definition. Okay, so if the domain of definition is operator from A to B, and this is the graph of function f. Okay, and I'd like to extend the domain as a closed interval. Okay, closed interval. And you must determine the corresponding value at both ends. Both ends. For that, for the function drawn over there can be extended as a continuous function, but that's not always true. Let's pay attention to this kind of example. Say suppose you have a function f of x is defined by x times sine 1 over x. Since x is not belong to the domain of definition, you cannot put 0. No, I should say 0. 0. 0 is not in the domain of definition. You cannot put 0 in the denominator. Okay? However, you can extend this function. If x is positive, you simply preserve the form of the original function. And if x is 0, you're going to assign the new value for it to make the domain of this extension is now include 0. Okay. Actually, the graph of this function, the graph of original function, okay, x times sine 1 over x goes like this. Okay. And we want to make this f tilde is continuous on its domain. To do that, your value, your extension value must be 0. Okay. By putting 0 here, we're going to have a continuous extension. This is not always true for a function like this. If g of x is sine 1 over x on a interval like this, then g tilde is an extension. Again, for positive x, you simply preserve the original form of the function, but for 0, we're going to assign any number, okay? For example, a. The graph of this function now goes like this. Okay, if you extend this function by adding any value a for number 0, okay, this is an extension. Okay, again, g tilde is an extension whose domain now includes 0, but this G tilde is not continuous. Okay? There is no value A, which makes this function to be a continuous function. Right? This is the distinction. If you can construct a continuous extension, this function allows the continuous extension by choosing value 0. But this function does not have any continuous extension. Okay? That property distinguishes the uniform continuity. Here, say suppose function f is defined on an open interval. And we know, no, this function is uniformly continuous. Okay? The uniform continuity defined on an open interval is equivalent to the existence of continuous extension. Tilde, whose domain now includes both endpoints. Okay, so if you can extend the function to be a continuous function at the endpoint, then the function is uniformly continuous. Actually, here in this example, we're not going to worry about the infinite. So let me just change this into a finite number. Okay. Of course, you should first you can also extend by adding the value at number 1 to make this as a closed interval. But here, in this example, just talk about the left hand, or the left endpoint. Okay, anyway. So existence of continuous extension is equivalent to the uniform continuity defined on an open interval. A function defined on an open interval. So this direction is actually quite trivial. If the extension f tilde is continuous on this interval, okay, the extension is continuous on this interval, then a continuous function on a compact set is automatically uniformly continuous. Or f is also f is just a restriction of this function. It's just to reduce the domain of definition. So this is also uniformly continuous. That's all. But for this direction, you need to think a bit. Okay, here we assume that f is uniformly continuous on open interval. So we need to define. Okay, let's only work on the left hand, the left endpoint A. We have to define f tilde A to make the extension. Okay, and so we want to construct a continuous extension. Okay, what's the corresponding value for the extension? So here the function f is defined on an open interval from A to B. The graph of the function, it goes like this. Then a continuous extension should have the value at this point a by taking the limit of this function, right? But here we have not discussed the limit of a function yet. So we're going to define this as the limit of a sequence f of Sn for sequence Sn in the domain of definition such that limit of Sn converges to A. So here we choose a sequence Sn that converges to A. Then evaluate the function f on this sequence, then take the limit. Okay? There are a few things that we need to worry about. At first, does this kind of limit converges for a sequence? In addition to the convergence, there are many different sequences. Instead of Sn, there is another sequence Tn that converges A. Okay? Then, is this a valid definition? You can define f tilde of A by using sequence Sn, or you can use different sequence Tn. Is that kind of approach is a valid definition, valid way of definition? If you define some concept or some function or some value with this kind of ambiguity, you need to prove the well-definedness. Okay, this is where you need prove the well-definedness. Okay, so by using this definition, you need to show the well-defined. Okay. For this kind of approach, well-definedness can be understood as the existence and the uniqueness. Okay. For the existence part, limit of Sn converges to A, which implies Sn is a Cauchy sequence. Okay, a convergence sequence is Cauchy, and Cauchy sequence converges. And since the function f is uniformly continuous, f of Sn is also Cauchy sequence. Okay, then a Cauchy sequence converges. So there exists a limit of f of Sn. But uniqueness is a different question. What if we have two sequences? You want to show? Here, as both Xn and Pn are sequences in the interval such that limit of Sn converges to A, and the limit of Tn also converges to A. Then, for those two sequences, Sn and Tn, what if we compute the limit of f, limit of f of Sn and the limit of f of Tn? They must be the same. Okay, so this definition, this quantity is unique, independent of the choice of the such kind of sequence. Okay, is it clear? Since we have two different sequences, Sn that approaches to A, and another sequence Tn also approaches to the same limit A. Okay, and by using the uniform continuity of the function, how can you verify those limits are the same? actually, you can construct a new sequence. A new sequence, let's say UN, by merging these two sequences, SN and EN. That means UN. This new sequence consists of S1 and T1, then S2 and T2, and S3, T3, S4, T4. Okay? By constructing the new sequence like this, those two original sequences, SN and TN, both of them are subsequences of this new sequence, right? Then, what's the limit of U? Since Sn converges to A and Tn converges to A, this sequence also converges to A. Okay? And by the existence, the limit of f of un. If you put the sequence un into the function f, this limit exists. Here we use this existence is derived from the uniform continuity. Okay, so this limit converges and f of Sn both f of Sn and f of Tn are subsequences of f of un. Since this sequence f of un has a limit, it converges to some finite number, then any subsequence should converge to the same value, right? That means limit of f of Sn is the same as the limit of f of T. They must converge to the same value. Okay? That's the uniqueness. Finally, this f tilde I defined by by using the extension like this. This f tilde is now continuous. Okay. This continuity is actually derived from the uniqueness. And the uniqueness. Actually, the original definition of continuity was based on this kind of approach. For any sequence that approaches to A continuous function should have the same limit. Okay, this way. Okay, so this is the equivalent condition for the uniform continuity of a function defined on an open interval. Okay, that's all about the uniform continuity. Thank you. Bye-bye.